Section 1.6, vector addition and subtraction. So oftentimes it's going to be necessary to add one vector to another, and it gets a little bit harder adding or subtracting vectors as opposed to scalars. With scalars, we can just add the two numbers, right? 2 seconds plus 3 seconds is equal to 5 seconds. Great. But with vectors, we have to pay a little bit more attention to the direction, because that will influence the addition. It's not always just adding the numbers directly. And we'll say that the resultant vector is the total displacement vector. So if we add one vector to another, then the net total we'll call the resultant vector. So let's check out an example of this, because examples make things a little bit clearer. So it says a car moved a distance of 5 miles due east. It stopped at a red light and then continued in the same direction for 3 miles. What is the magnitude and direction of the car's resultant vector? So this is where a picture is really useful. We know that east is pointing to the right. So that's what we want to focus in on here. And so we can draw this out, that we have the car going a distance of 5 miles to the right, east, and then it stops, and then it continues on in that same direction for 3 miles to the right. Now, the net resultant is going to just be the combination of these two, because they're pointing in exactly the same direction. They just keep going to the right. So in this case, it is simple addition. 5 plus 3 is equal to 8. A few key details here. When we work to get the resultant vector, when we go to draw it, this one's a simple example, but it will get more complicated. We first want to make sure that we line the vectors up tail to head, or I've also heard it described as tip to tail. It's the same thing either way. What is that saying? Well, it's saying that the first vector, the very tip of that, should be pointing to the tail of the other. The arrow of one should line up with the starting point of the other. So once you've made sure that you have the vectors that way, that they aren't like pointing at each other or have the two arrows next to each other, but that you have an arrow next to a tail, then you can draw the resultant from the very first starting point, the original tail, to the final arrow tip, to the final finish. So that's where you will draw the resultant vector, r, which in this case is 8 miles. Right, so there's one example to get us going on this. Let's try another one. So it says Miguel walked a distance of 6 meters due east, then he turned left and walked for 2 meters due north. What is the magnitude and direction of the resultant vector from his walk? So notice this one is now a little bit more complicated, because Miguel is not just going in a single direction, due east. Miguel has 2 different directions. So this is where we want to draw it out very carefully. So 6 meters due east, we remember east is to the right. So my 6 meters, cool. And then at this point, Miguel turns left and goes 2 meters due north. So north is going to be in the upward direction. So I could fill that in here. And the vectors automatically, if you just sort of follow it like a path of the person, they're already lined up so that the tip of one is pointing to the tail of the other. That's a great news, because it means we can now draw our resultant to start at the original tail, the original start point, to the final tip. That's our final end point. So we're going to connect those 2 dots with the arrows lining up. So that gives us a picture of how we could do it, right? And that's shown here in this figure where they went through this. Now, we could actually also get the numbers here, because it says to find the magnitude and direction of the resultant vector r from the walk. So if we want to find this value of r, well, if we want to just get the magnitude, we know the magnitudes of the other 2 sides of the triangle. So how can we relate the 3 side lengths of the triangle to each other? That's right, it's our Pythagorean theorem, right? So we can take 6 meters squared plus 2 meters squared, sorry, my writing is so messy, is equal to r squared. And so we'll take the square root of both sides, and be careful when you take the square root of the numbers on the left here. You can't just cancel the square because there's addition in the middle. So that is going to throw off the results. But this is something that you could then calculate out, right? So 6 squared is 36, plus 2 squared is 4, so 40. And you need to do that addition before you take the square root. And then when you take the square root, you should get, looks like 6.32. What would the units be? Because we need to make sure we keep our units there. They're going to be meters, distance. So this gives us the magnitude. What about the direction? Well, direction, we remember, is going to be finding this angle theta. And we could do it in terms of the resultant, but since this is a decimal and since it's something we solved for, it might not be right. It's best to work in terms of the known given quantities, which are very precise. So this looks like another example that involves the opposite side and the adjacent side, not the hypotenuse. What trig function will that be? That'll be our tangent, or inverse tangent, to get the angle. So theta is equal to inverse tangent of the opposite side, 2 meters, divided by the adjacent side, 6 meters. And so inverse tangent of 1/3, 2 divided by 6. That looks like 18.4 degrees. So double check that you get this result. Make sure that that all makes sense to you. Here they show the work. This is the magnitude of the resultant vector walk, right? Similarly, we can go on to get the direction of the resultant vector walk. So that's how we solve for both the magnitude and the direction. The magnitude alone isn't meaningful unless you have the context that's the magnitude of this resultant vector of the walk. All right, so that's vector addition, right? Where we had it both walking in the same direction, then walking in one direction and walking straight up at a right angle to it. Let me pose a different question. What if the vectors aren't parallel, aren't pointing in the same direction, or perpendicular, where it's exactly due east and due north? What do we do then? Well, we can follow the same procedure of lining our vectors up tail to head, and we can at least draw the resultant vector. So we have vector A here. Vector B is no longer going straight up, it's kind of up and at an angle. And our resultant vector C is going to go from the very original start to the final finish. That gives us the resultant vector. So that's what we'll do. We will get to see how we can do this other than graphically. We can break it down into components to be able to add it, but that's coming in a later section. So stay tuned on that. Just know that that is coming. Now, we've talked about vector addition here. What about subtraction? Have to keep that in mind too. So here's the rule. When a vector is multiplied by -1, the magnitude of the vector remains the same, but the direction of the vector is reversed. So this is the way that we deal with vector subtraction, is instead we treat it as a negative vector. So instead of writing it as vector A minus vector B, which minuses are hard, we want to stay positive, we can write this as vector addition of vector A plus a negative vector B. This is a reframing to keep things more positive, to focus on our addition rules. And all that we'll have to do in order to accomplish this is flip the direction of vector B. And that's what's shown here, right? B is originally going up and to the right, and then negative B is going down and to the left. So let's try some examples of this because I think it will help make it clearer. So first, if we want to add A plus B, we have these two vectors, A plus B. I encourage you to draw them on your page, see what you come up with as a resultant. So go ahead and pause and do that. Okay, I'm going to hope that you did that. Now with vectors, as long as we keep the orientation, the direction the same, we can shift them freely however we want to. So there are a number of different ways you can shift it. I'm going to focus on keeping A the same and just shifting my B to be along the same direction, but so that the tail of B is instead at the tip of A. So I'm going to draw my vector B up here. Vector B, awesome. Notice the direction is the same, the length is the same, or it should be, not quite perfect. And then we can draw our resultant of A plus B is going to be from the original tail to the final tip. So that gives us A plus B. Awesome. And that's shown with a little more accuracy, so I'll clear my drawings. So we have A plus B there. Great. Now, what if we want to do A minus B? And we'll assume that B is in the same direction. Well, minus B is just going to be the exact opposite direction as this, right? It'll look something like that. So we're going to do A plus a minus B. So this minus B, I'm going to fill in over here next to the A so that the tail of it is at A. This is my minus B. And I can once again draw my final resultant vector from the original tail to the final tip. And now my resultant does look very different, right? Since it goes from A to the final arrow of minus B. The resultant is now pointing fairly levelly to the right as opposed to much more up. And here's a better picture than what I had. So A plus minus B gives you this resultant vector. All right, so that illustrates some of the ideas. I encourage you to try this yourself, and let's try it ourselves. Let's get some practice with a think, pair, share of vector subtraction. So which figure, which of the options, shows 2A minus B? This one's a good one. So I encourage you to think about this, come up with an answer if you have to guess, but think about for some time and at least pick something. So go ahead and pause the video now. Right, did you do that? I'm hoping so. All right, so as we look at this, first off, there's this 2A. If it's 2A, then it's going to be the same as A, but it's going to be twice as long. I'm going to draw the magnitude of 2A, something like this. All right, and then we have minus B, or plus a negative B. So that means my B vector is going to have to point in the opposite direction. That would give me my minus B vector. Now, if we want to add these, right now they are tail to tail. So I cannot draw a resultant at this point. But I can shift one of the two vectors, and I'll shift the A one just to be different. So I'm going to keep the negative B there, and I'm going to shift my A so that it has the same orientation, but that the tail of it, or shift the 2A, is at the start of B. So that is 2A. It is still the same. I haven't actually changed anything. I've just shifted it over. That's not changing anything. And now I can draw my resultant from the original starting point to that final finish. And this one looks the most like A. All right, so there we've gotten to see some vector addition as well as vector subtraction. And in the next section, we'll get to take a look at the components of a vector, or in other words, how we can truly break a vector down.